exponential functions. We're kind of developing them a little further. We're going to take a look at what happens when maybe I'm considering a time period where my function is changing by doubling or halving or something like that. And how does that relate to a per year change versus a per time period change? So that's what we're going to look at as a new equation that helps us develop how do I take something that's not happening on a yearly or considered as a yearly change and make it become a yearly change. So before we do that though, let's see if we can just write our exponential function. Given some points, we need to create something exponentially out of this. I could do this if it said linear function, quadratic function. I could do this with any of them. But it specifically asks me for exponentials, which means I'm going to have to start with this generic tool that I can plug things into and then come up with my new value. When you write exponential functions, you need to fill in something for A, and you need to fill in something for B. So they give us coordinates, 0, 5, for this f of 0 equal 5, and 3, 40. And with 2 points that are on this curve, so you can imagine I've got graphically what's going on is I've got some exponential growth thing happening. 0, so it's looking something like that. And we're right now at 0, 5 and 340. Let's say that's 340. And we're trying to fit an equation that matches that curve. Well, ideas? Plug in. Exactly. What do I plug in for? Y's and x's. Very good. So these are y's and x's, so I can take my y equal abx. And we can plug in my y of 5, my x of 0. And we get 5 is equal to ab to the 0 power. And I find a. Yes. A would equal 5. Because b to the 0 is just 1. Then we do the same thing. Because I have 2 unknowns, I'm going to have 2 equations. So there's one of them, finding a. And then I have another y equal ab to the x. But this time y is 40 and x is 3. So 40 is equal to a, which we know is 5, b to the 3rd power, and solve for b. So b cubed would equal 8. Take the cube root. And we discover that b is equal to 2. So now I have all my values of a and b that I can then write in my equation to get y would equal a, b, x. Yeah. No, that's not. That's just exponential. Yes. Yes. Oh, good question. Good question. Think of order of operations. Can I multiply the 5 and the 2? No, I got to keep that 2 with the x. So those 2 stick together. Base and power. We got to leave it like that. Oh, that's not a hand. Hands? Hands. Yes.
How did you get 8?
How to get 8? So did you see plugging in 40 for y and 3 for x? From the previous equation, we found a is equal to 5. Plug that into the a is the blue equation. Divided 40 by 5, got 8. And then the cube root. Yes?
I mean, you can just leave it like that, but it wouldn't be like hypothetical.
Yeah, you can leave it like that. You could write it as f of x. Either way works. All right, there we go. That's one of our unique exponential functions because our b is 2, so we call these doublings. These are doubling exponentials. Yes, ma'am.
Would they always give you an f of 0?
That's a great question. No. What if they didn't? It still would work. If they didn't give me an f of 0, they gave me an f of 1 equal 5. I'll still have 2 equations, except now I'll have one equation that has an AB in it, another equation that has an AB. I I choose to solve for A, and one of them plugs into the A of the other, and then I find B, and then go back and find it. Does that make sense? It's just like a system block. You got a system, you have X's and Y's, you choose one of them, you find an X, plug that in for the X, find Y, and then you plug that back in. So yeah, it doesn't have to be 0, 5. But if they do give you a 0, 5, 5, or whatever that number is your A value for an exponential. Good question. All right, why don't you guys try that one, see if you can come up with that equation. Oh, crapper! Oh no, that's good. Thought I pressed the phone. All right. That's all right. No worries, no worries. That way we get 0. Oh crap. We get 4. We get 4, 5. So here we're gonna. There's my A. And then I'd have 5 is equal to A B to the 4th power. So divide the 5 by the 80, and we get 1/16 is equal to B to the 4th power. And then now I'm undoing that for the 4th root. And the 4th root of 16 is 2. So we have 1/2 is equal to B. Therefore, Y would equal 80. There's my B to the X power. Okay, that's a great question. Would these represent problems that are per a yearly time period or days? And the answer would be yes. So what we're going to go do now is we're going to look at what happens when I don't have information as per year. And then we're going to see how we can make it. We're going to make it adjust back to a per year problem by doing a little tweak. That's what we're going to do next. All right, are we good on that? Okay. So here it is. That's a great lead in, Michael. How do we take problems that don't present themselves as a per year change and make them become a per year? So here's our, right, adding to my formula sheet or flashcards or whatever it is that you guys are doing. Here's the next one I'm going to have to add to it, and it's this equation right here. It's B to the T over K power, or B to the 1 over K power to the T power. We'll talk about how we get that. And how this allows you to write it as a per year, per month, per day, whatever it is that you're setting up your time period. Less. So generic y equal ABX. Then we developed a little more formal exponential function of A of t equal A sub 0, 1 plus r to t. That, remember, could also be 1 minus r if it's decay. And then we go to this, kind of looks like the one above, A, B thing, but you got this t over k. And so here's the scenario that we've been presented with. We'll come back and talk about the formula in just a second. We've been presented with this scenario where we're going to double, that's important right there, we're going to double our money, and we're going to do that in 12 years. So what's happened here is I've been given information that happens over a span of a 12-year time period, not a yearly time period. And I'd love to be able to find information on a yearly time period so that I don't have to wait every 12 years to know what my money's going to be amount-wise. So we're going to be able to write an equation that allows me to figure out how is that change happening on a yearly basis so that I can know, oh, at the end of 5 years, here's how much money should be in my account. Right, so it has to do with this B and this T and this K thing. So the K value is the amount of years, days, whatever the time period is, that it takes for me to do something to my initial amount. Double it, half it, whatever that is. However, I'm changing my initial amount. So here's what you're doing. You're changing A sub O by doubling. How long does it take to do that? Is this value, and that's what K is. K is the time that it takes for you to change your initial amount by whatever it is you're doing to it.
So if that was like half a year, we could do 0.5.
Yeah.
So this equation is all relative to a year. So
Well, or days. This one happens to be years, just because it says 12 years. But I can use this for a bacteria problem in a biology class, right? Where usually things are happening on a daily basis. I could still use it. but now it's per day versus per year. So that doesn't matter. A time period could all be here. That answer your question? Yeah.
So the kilowatt's going to open
Yeah. So here's the deal. Think about why is it going to be this 1 over k thing. So I know that in 12 years I'm doubling my money. And I want to know on a yearly change what's happening. Well, in 12 years I'm doubling, that means in 1 year I've got 1/12 of a change, correct? And in 2 years I have 2/12, and 3 years I have 3/12. So that's where this 1 over k thing is coming from. That is coming from the fact that I've got, in this case, a 12-year change, and I'm doing that on a yearly basis would be 1/12. And then I'm multiplying it by how many years that I'm working. Yeah, exactly. So that's what we have. You have to look at these problems, and they're not going to be like, hey, use the BTK. No. You're going to have to figure out when to use them. And you will use them when you have a change of my initial amount. That's the key. How am I changing my initial amount? And how long is it taking to do that? That's when I have a BTK problem. So is this a BTK problem? Yes or no? You can't answer because you already heard the example. I buy a car. It's $15,000. It appreciates 5% per year. What, at the end of 5 years, how much is it worth? Is that a BTK problem? Why not? Okay, because I have an initial amount, but more importantly, because of what? I told you how it's changing. How is it changing? 5% a year. If I had the same problem, I said it loses its value, it gets to half of its value in 7 years, now it's a BTK problem. See the difference? Okay. Here's my initial amount, it's changing by this much in this amount of time, BTK problem. If I don't tell you that, it's not a BTK. Alright. So we go, we set this thing up, and it says we want to write it in each of the forms listed above, meaning that form and the one next to it there. So we've got our A sub O. We don't know. But we don't care. We're just going to use this in the equation. We know that K is equal to 12. And I know that I'm changing my amount of K. I'm doubling it in 12 years. So our B value is going to be equal to our 2. So we set up our generic. A sub T equals A sub O, and then we have B to the 1 over K to the T power. Now, remember that that is the same thing as A sub O 1 plus R to the T power. So what you see here is that this B 1 over K and this 1 plus R are the same thing. One of them is just if I know how my rate is changing on a yearly basis, and the other one is not. I don't know how it's changing on a yearly basis, but we can find it. All right, so we plug everything in. We'll stick with this one. So we have A sub O, B, I'm doubling. 1 over 2, or 1 over 12 is my K. And I get that. So now, we can figure out what does my change per year look like by going 2 to the 1/12 power. So 2 to the 1/12 power, somebody did 1.05 what? 1.059 to the T. So the question was, express AT in each of my forms. This would be the per year form. I know that I'm increasing this amount of money 5.9% every year. So that's it. And then my other, well, from that I can figure out what my R is, right? Because, again, this little piece is the same thing as 1 plus R. And if that equals 1.059, if I subtract 1, I get 0.5. No. Boy, wouldn't that be nice? I get a rate of 0.059, which is my 5.9%. That's how I can come up with my R if I need to find it. So I have that form, and then if I wanted to leave it in this form, 2 to the 1 over 12 t, or if I put the t back in there, that's fine too. So that's expressing it in my one of them where I go yearly, the other one where it's, no, I just didn't change it to a decimal value there. If I wanted to express it as a what happens every time period, I've got this. 2 the t, but my t would be every 12 years. So that's where, again, this concept of the time period gets a little tricky sometimes. Sometimes it's representing one, sometimes in this case it would be saying doubling, but it's happening over a 12-year time period. Yeah?
So what's the difference between 1 plus r and b over t over k?
What's the difference between...
Yeah, what's the difference between using 1 plus r or b over...
So what's the difference between these two right here, these blue?
Yeah.
They mean the same thing.
Like, if you're expressing different time periods.
Oh, I'm expressing different time periods? Okay, so back to this. So if I express the problem like this, that problem would have to be understood that my t doesn't represent a per year thing, but my t represents every 12 years. So that means if I knew I've gone 36 years in my bank account, I plug a 3 into this t, that's going to give me my answer. If I instead wanted to use my per year change, then I have this guy. I can plug 36 in for that t, and I'm going to get the same answer. Well, I'll get something equivalent. It might be off a little bit, but because of the decimals, but they're going to give me the same amount. Fine. Yes.
So if you're going to use that, the second way of doing it,
Like that way?
yeah.
Yeah.
You'd have to make it a let statement, say that like t equals 12 years.
Yeah, if I'm going to use this, I'd have to make that a statement. That t is representative of a 12-year chunk, not a per year chunk. But we're gonna often, well, I should say 99% of the time, we're going to be rewriting it on a per year basis so that I can, because like I said, I don't want to wait until every 12 years to know what money does in my bank account. It'd be nice to know what's happening on a yearly basis. Yeah. Yeah.
Would you use 1 minus r there?
Yeah, exactly. Yeah, that'd be 1 minus r. Yeah. If it was a decay problem. Good questions. All right. Rule of 72. All right, so this works when we are doubling something. Doubling. We're not going to derive where it comes from. We're just going to have it at our disposal. More of an FYI than anything. So if I know that I've doubled my amount, like that last problem, we knew that we were doubling in 12 years. If I were to have taken that 12-year time period and I divided 72 by 12, it would have told me what my per yearly change was. And then if you look back at that problem, weren't we pretty close to 6%? It was 5.9, wasn't it? But it was pretty close to 6%. So this is a good estimate that I could use to figure out how many years is it going to take for me to double my whatever it is. We're doubling the number of items or doubling money. I can just do 72 divided by whatever that rate is. Now the difference in here is we've been working with rate as a decimal value. This is rate as a percentage value. So that number would just go right in there. So 6%. Right? So when I get my answer, it's going to be a percentage. So if I did that 12 years, 72 divided by 12, that's a 6% answer, not a 0.06. convert it to that. You're going to get your answer in percent versus decimal. Can I do that? Like our last problem. Yeah, we can go back to this one. So we can apply, because on this problem I'm doubling, and I know how long it takes to do that. I can apply the rule of 72 for this problem. The rule of 72 would say that 72 divided by the 12 years that it takes me to double my money says that I have 6% change per year. But, you know, it's pretty close to ours, which is 1.5. That's it. So only for doubling. Doesn't work with other ones. All right, where were we? Where were we? Back there? Yeah, that's where we were. All right, so how long? Certain bacteria grows at a rate of 12% per month. How long will it take for the amount to double? Answer. Six months. Yeah, it's going to take 6 months for this to happen. This is a rule 72. We're doubling, doing that on a monthly thing. You got a rate of 12%, so here we had a rate given to us. Oh, that's bad. Don't use green on green. Can't see it. What color is the left slide? The last slide.
Yellow.
They're all the same color.
Except the last one.
Oh, you mean the last slide? Yeah, the last one's yellow. Always last one in yellow, so I know where to stop. You know? Brilliant of me. All right, so my rate is 12%. So I can go in and say 72 divided by this 12 is going to tell me that it takes me 6 years. Oh, yeah, thank you. Yeah. Because we're not talking about you, we're talking about months. There we go. Yes, Julius.
So when you're using the rule of 72, you're going to be left with months in your answer.
No, you're going to be left with, that's a good question, you're going to be left with whatever this is. So that was 12% per month, it could have been 12% per day. So whatever that unit of time is what you will have as your answer. All right, again, more of an FYI than anything. Here, though, we get to a good little problem. This is great. Not just a good one, this is a great one. All right, we doing all right so far? Any questions before we roll on? All right, this one, for the answer for, let's see, part B, which would also then be affecting the answer for part C. There, I'll talk about a couple different ways you can think about this. So, but first, here we have number of hours that we have our bacteria kind of hanging out, doing their thing, and there's the number of bacteria. Now, who's the person who counts them? Who counts that bacteria? I want to know that. And how do you know? What do you mark them? What? Bob, are you here? Joe? How do you count bacteria? I guess you can. They're all probably moving around. Stay still. Anyway, that's little sidebar. Anyway, we've counted these things, and this is how many bacteria after each of these chunks of hours. So, what has happened between the 3rd and the 9th hour? How has it grown?
Exponentially.
Okay, good. You guys are on. It's exponentially grown, but specifically it has tripled. I know you did. I heard you. I heard you say that.
Yeah, you saw this.
It's no fair.
I didn't even pay attention.
Of course
I
not.
swear I was doing my homework.
All right. So do you guys see that? I've tripled, right? 260 times 3 takes me to 780. So in that 6-hour time period, so in the 6 hours here, I have done that. tripled. So here I have a situation, yes or no, that I can BTK. What do you think?
Yeah.
I like it. I don't know. That's a very informal way of talking about our per year change. But yeah, I can because I've tripled an amount, and I've done that in 6 years. And so now it's a model. We're going to say that that model continues for the rest of this exponential growth cycle. I'll double it every 6. So we can say I've got a K value of what? What's our K value of this problem? Do you remember what the K is? It's the time for what? 6.
6 hours.
For your change of your original amount to happen, right? So we know we've tripled. We've done that in 6 hours. So this is my K. That's my K. This, what's this? Huh? B. You're right. That's my B.
Is it 3x?
No, I did that to just be 3 times. But yeah, our B is 3. Yeah, I should probably change that, huh? 3 times. So my B is equal to 3, my K is equal to a 6. So how did the population change from 3 to 6 hours? Well, we've already said that it went from 260 to 780, so we've tripled. Now, here's where it can get a little interesting in finding our equation. So the very first thing we did was we were given 2 points, and we used those 2 points to write an exponential equation. I have 3 points that I could use to do this. 3 to 260, 6 to 450, 9, 7, 8. All right. One of the things I could do is simply knowing, well, let's start out with our formula so far. We know this. Now, I don't want to average them. I don't want to do that. So we know so far that our amount of population as a function of time, if I just think about my generic formula, right, there's the generic one, but because we recognize that I'm tripling my initial amount, and I'm doing that in 6 hours, then I could set this thing up as P of T is equal to A sub O 3 to the 1 over 6 with a T. I could do that. You guys agree with me? Yes or no? Yeah? Yes? Yes, ma'am. Why is the B 3? Good question. The B is 3 because that is my growth factor in this 6-hour time period. I've gone 3 times as much.
She always wants to.
This T over here is just representing a time period, and in our case, what does that represent for this bacteria? What is T supposed to be? Huh? Is it? Look at the chart. An hour. So that's an hourly change. Right?
So it's not always.
It is. This is going to be coefficient in front of that right now? Yes, that's a 1.
No, the one on top of the K.
Oh. Yes, that will always be a 1 on top of the K. What? 3 to the 1 6. Who's got that for us? Oh, what is that? So this, remember, that this value is the same thing as that. It's your 1 plus your 3.
What's
Oh, your generic. Oh, that's what we've got right here. It's P of T is equal to A sub O, B to the 1 over K minus T. That's what we got set up. So who's got it? 3 to the 1 6. 1.201. All right. So I know that P of T is equal to A sub O, 1.201 the T. is our change on an hourly basis, not on a per 6 hour basis. If we're on a per 6 hour basis, it was just 3 to the t. It's safe to use 3. I mean, I'm fine to use 2. This would have been my equation on a 6 hourly basis. Okay, but we're not quite there because we need to find that A sub O. All right, so here's the deal. Listen, I'm changing every 6 hours. Every 6 hours I get a change. Well, look at. Remember how I said you can pick any of these points? You pick any of those points and plug them in, you might get a different value of A sub O. It'll be slightly different, a couple decimal points off. We could just do this. Why can't I just consider this value? Because if I'm changing every 6 hours, well, that tells me after 6 hours how much bacteria I have. That can be what I plug in to find my A sub O. All right. So we've already got the number here that we're working with. Every 6 hour change, that's how much I end up with. Well, how much did we begin with? So if T was equal to 6 hours, then we can say that T is 6 hours, which we know, according to that table, is 450 bacteria, is equal to the initial amount of bacteria, which we're trying to find. And then I can use either the 1.201, let's just do that one, 1.201, then this is happening for 6 hours. So we can go ahead and find A sub O. Somebody tell me what 1.201 to the 6th is. Great. Of course it is. Because that's what that number is. A sub O times 3. So we get A sub O equal to 150. Right, there's our initial amount. Now again, had I used another point, like I think if we, I think somebody, last period we used the 3 and the 260 number. I think in that problem you ended up with like 150.24 bacteria. Well, we can't have 2/4, we can't have 25% of the bacteria. So we would round it, we rounded it down to the nearest whole number of bacteria, which would have been the 150. So you're gonna get a slight difference in your answer depending on which value of those points you choose to use. And as long as your work's all there, you're stating, what my assumptions are, assuming I'm going to use 0.3260, and I do my work off of that, and if all the work's right, your answer's different than your neighbor because they use a different point, it's okay. It's all okay. The process is right, and you guys are understanding the concept, which is really what we're after. So now I can finally write, we still haven't answered part B, have we? No, so here now we're going to answer finally the part B. The population of bacteria is equal to 450, and then we'll do the 1.201. There it is. Here's my population on a yearly or an hourly change. No. Part C now says how much bacteria is there after 24 hours or 1 day.
I thought we got the initial value.
Oh, yeah. Why did I write 450? Should be 150. Thanks. Yep. All right, there we go. So now part C. What's the population after a day? Again, mixing my units. I got to remember that a day is equal to 24 hours because that's the information that was given to me, and that's the information that my formula is set up in hours, not days. So I have to make sure I plug the right stuff in. 24 for my T. P of 24 is equal to 150. 1.201 to the 24. Yes.
If we use the other one,
Oh, look at about ready to say this. Go ahead, tell me. All right, so here's the question. Are they the same? Brooke used the 6-hour change formula, and we know that in 24 hours, we have 4 6-hour change periods. So she sets it up with 153 to the 4th. Is that the same thing as 1.201 to the 24th times 150? The answer is yes. It is the same. Although your numbers might be a little different. Are your numbers different? What did you get over here? 12,150 bacteria here. How many did we get here?
12,165.
Say it again.
12,165.
For this one?
That's what I got.
12,165. Is that right?
Yeah.
Get confirmation on those?
Yeah.
They're a little off. They're a little off. This is more conservative. That's more of a conservative answer. No, I won't mark you down. But the only reason Brooke could do that is because 24 hours happen to be an increment of our 6-hour change. If that was a 5-hour change, she couldn't do that. You understand that? Yeah. All right. There we go. It's a good problem, good problem. Any questions? What's up? As the exponent, could I use a decimal? So could you do 24 divided by 5 and get a decimal? Yes. Technically, can do that. All right. So here it is, last one. You guys tackle this one. Look at this, Twinkie. We had a good discussion about Twinkies. Let's freeze. So we'll freeze ourselves here. So first of all, we set our generic. Remember, the more often you write this, the better it's going to be in terms of, well, the faster you'll memorize it. So write the generic down. You're setting up a form of communication where you got to let everybody know what's going on. So there's where I start with. I don't know how much the Twinkie is after it's gone through its 7 years or however long. I don't even know how much the Twinkie was when it started. But I'm not looking for that. I'm looking for what rate does it change on a yearly basis. And all of that information is right there. So we say A sub O, leave it. B, I'm having value of the Twinkie. I'm doing that every 7 years. And so remember that in this formula, that the B to the T over K is the same thing as our 1 plus or minus my R. So somebody is going to tell me what 1/2 to the 1/7 is. 0.905. And that is equal to 1. What is it equal to? 1 plus or 1 minus R? Because it's less than 1, it's a decay, so I have a 1 minus R there. And then I got to solve for R. So I can just subtract 1 over here and divide by negative, and I get that R is equal to a 0.095. Is that right? Or a 9.5% rate of decay every year. And I am probably going to venture out and suggest that that is actually too big for a Twinkie. I bet it doesn't do that. I bet it's less. But anyway, there's how you're going to find your rate. It's just that B, T over K thing.